So in this video, we'll be finding the moment about point A. And in this video, we're going to go over two methods. The first one is going to require deducing unknown line segments, as well as extending the line of action, which is the 4 kilonewton force being pulled 60 degrees about point C. And we know that generally the moment about a given point is force times the distance, but we don't really know the distance. So where do we go? Well, when it comes to these problems, the first thing to do is to extend the line of action. And do we have any additional 60-degree angles? And if so, where? Turns out we have one right next to point B, and as trigonometry goes, there's an equivalent angle on the other side of it. But we also get something else, and that is a perfect right triangle. Now, let's be a few steps ahead, yeah? And let's think about what we have. We have the intersection between the line of action and the line segment AB. Let's toss in an arbitrary point E, and let's think about these line segments where we have EB, AE, and we know the total line segment of DC is 4 meters. Let's see here. What significance are these two line segments? Well, let's see. We have the line segment EB and 60 degrees, and AE is going to be 4 meters minus whatever magnitude EB is. And if we get those, could we find the moment about point A? Let's do that. So we have 3 over EB, which is equal to tangent 60. You can use cosine or sine, but you're going to be left with two unknowns. So going with tangent optimizes our chances of solving this problem. And once you plug that in, you should get a value of 1.73 meters. So that's our line segment of EB. And AE is simply the 4 meters minus whatever we just got, the 1.73 meters. And as a result, we get 2.27 meters for line segment AE. Now, this is where the line of questioning helps, because we know the moment about point A is force times distance. And the distance is going to be deduced from what we just got. AE, the 60 degrees, and the missing D. So let's use some trick where sine of 60 is equal to D over line segment AE. By solving for D, we get the value of 1.96 meters. And now we have both the force and distance. Now let's not forget the standard convention that counterclockwise is positive. So let's put that in our calculation. And what do we get? 4 newtons times 1.96 meters. And we get 7.86 kilonewtons, kilonewton meters. Now, earlier in the video, I said there was how many ways to solve this problem? 2. At most 2. And this method requires finding missing line segments. But is the second method a lot shorter? Well, it actually is. So let's say we have these two x and y axes, and we want to find the horizontal as well as the vertical component of the force. And to find the horizontal component, it's just going to be 4 kilonewtons times sine of 60, which is going to yield 3.46 kilonewtons. Now for the vertical component, it's just going to be half of the force, since it's cosine of 60 times 4 kilonewtons. And using the same moment equation, once again, counterclockwise is positive, moment about A, and that should equal the difference between the horizontal and vertical component. Go ahead and plug that in and see what you get. You will notice that the answer is not similar to what we did earlier, but it's the exact same output. So the difference is 0 between the two methods. And you'll notice that one requires significantly less work than the other. Once again, It's all a matter of the cards are dealt with. You may or may not be tasked to find missing line segments, but if you are, it helps to employ a basic trig and knowing, well, everything else.